Here we're going to take a look at nucleophilic substitution reactions in haloalkanes. And haloalkanes, I'm just going to draw the general structure. And I'm going to draw a primary haloalkane, and I'm just going to put Br- as my halogen. Obviously this halogen here could be any of the halogens F, Cl, Br or I. Now, haloalkanes can be attacked by nucleophiles because of this polar bond and this delta positive carbon then and delta minus bromine. The nucleophile then can attack. This nucleophile here is attracted to this delta positive carbon and can attack this here. So it's the negative, the lone pair is attracted to the delta positive carbon. And as far as A-level goes, at least, you need to be aware of 3 nucleophiles. Obviously, it can be attacked by a variety of nucleophiles, but we're just going to look at 3 nucleophiles. So, nucleophile 1 is hydroxide ions. So, what we get then is we get this haloalkane is attacked by hydroxide ions. The key here to remember is the conditions required. And for nucleophilic substitution to occur, these hydroxide ions must be in an aqueous solvent, in water, dissolved in water, so usually just a solution of sodium hydroxide. So what we get then is our hydroxide ions, and the key is lone pair on the oxygen, negative charge on the oxygen, and we get then attack from the lone pair to the delta positive carbon, and then a breaking of the carbon-bromine bond. Remember, when bonds break, the pair of electrons go towards the most electronegative atom. That then is we're drawing this, as we call this, an SN2 mechanism. It's a one-step concerted mechanism where bond breaking and bond forming occurs at the same time. And that then will produce our alcohol. So what we get then is this CBr bond is broken and the OH takes its place, and that gives us an alcohol. So if we were to write an equation for this, and again, you would never ever include the sodium in the mechanism, then we would have and the bromide ion then just tags on with the sodium and forms a sodium bromide. The next is cyanide ions as a nucleophile. So we get, again, we basically get exactly the same. And just to show you, we can basically just copy and paste this in, and instead of putting hydroxide ions, we can just put cyanide ions, and the mechanism is exactly the same. And again, we can do the same there. We get the same product, or similar products, but instead of an OH, we have a CN, and that is a nitrile. So that's the key there. We form a nitrile, just to show this carbon is triply bonded to the nitrogen. It's a nitrile. And this is a really good way of extending the carbon chain by 1. See, we've got an extra carbon in the chain. An equation for this, again, we would use sodium or potassium cyanide for this. So again, we just simply just get rid of the OH, put a CN. Again, get rid of the OH and put a CN. So we extend the carbon chain by 1 and form a nitrile. The third nucleophile we can look at then is ammonia. And again, the ammonia, in order to form the product that we're going to show here, the ammonia really needs to be in excess for reasons which we'll discuss at the end. Again, we can just copy this because the first part of the mechanism is just the same. This time, it's important to remember we've now got a neutral nucleophile, so the mechanism is going to be slightly different. So we get this nitrogen attacking the delta positive carbon, and now we get an intermediate structure because of this neutral nucleophile. We now get an intermediate structure. So we get a nitrogen now, and again we've still got 3 hydrogens attached. Nothing's changed there. We've still got these 3 hydrogens attached, and the important thing is we need a positive charge on that nitrogen. And then what happens is one of these nitrogen hydrogen bonds break, and that gives this nitrogen its lone pair back. And what is actually pulling this off is another ammonia molecule. This is not a marking point, but what is actually happening is this. So you form a new NH bond. This forms an ammonium ion, and then this gives this nitrogen here its lone pair back. And what we get then is an equation where we actually now need 2 mole equivalents of ammonia. And that forms an amine, a primary amine. And my other product is ammonium bromide NH4Br. Now, an important thing to remember is the product formed. We'll just draw the product formed here. The product formed is an amine. So we get rid of that, we put an NH2. And the reason the ammonia needs to be in excess is because if the haloalkane is in excess, then the amine has got a lone pair. And if we've got an excess of the haloalkane, then the amine can also act as a nucleophile and attack the electropositive carbon, the carbon with the plus charge, and that will lead to further substitutions. Potentially, if you've got an excess of haloalkane, you will get a quaternary ammonium salt, and that's explained in the video on amines and amines nucleophiles. So that there is nucleophilic substitution of haloalkanes.